Perfect. Yeah. Hi everyone. Good evening, everyone who is here in a room, and hello everyone who is listening online. As always, guys, online you're just missing here pizza, you're missing beer, you're missing a lot of cool stuff. You're missing actually the first row, which is absolutely free here to join. And what we gonna start is our Apache Iceberg Meetup Community Europe. My name is Victor. I am actually the one who started the whole initiative, and I'm very glad here. First of all, to say thank you to Fivetran and to Snowflake to co-host the event. I hope you enjoyed the pizza, and I hope you enjoy the venue. And it's actually for us, for the Community Europe, the first time we are here in Ireland, Dublin. And glad to see that there are people here who is interested in data, not in AI. So thanks for choosing Apache Iceberg Meetup. Well, we do have some quite interesting talks today about, well, guess Apache Iceberg, right? So we're gonna listen about some historic overview, how we got actually to that situation. We're gonna listen about how to ingest data, how to improve some analytics on the data, how something like catalog plays a role. And the only one thing what I would love to inspire you, everyone who is here in the room and who is listening, to apply maybe next time to be as a speaker here. So you're all welcome to support the community. And as you can see, I'm just trying to kind of put green lights here on a map. So I'm just trying to build a European community. Thanks for our American sponsors here. We have a lot of events in America, but we don't have that many events here in Europe. As you can see, we have yellow colors, which means that's where the places where the next meetup will find place. In May, we have some events in Spain, Barcelona, and Madrid. So guys, think about that. So you can go to your boss and say, well, I have a topic to talk at a community, and that's next month in May. All right, so, and right now, I would love to pass over to you, Andrew, and then we have our first speaker.
All right.
Thank you.
Thank you so much, everybody, for coming. Unfortunately for me, normally I speak in front of audiences where maybe English isn't their first language, and I think they give me a benefit of the doubt because of that. Unfortunately, it's not. You can see through my issues. So I like to go first because when you go to a comedy show, you've got the opener, and the opener's usually not that good, and they set it up for the all-stars, right? I'm the opener. So that's what you've got to deal with here. So I'm going to talk a little bit about Iceberg and how it can integrate with agents. And so we've been hearing all about AI, and we also hear about Iceberg, and is there crossover, is there not? And we'll clarify that a little bit. So I'm one of the co-authors on the Apache Polaris book. So feel free to get a free copy of this if you want. Jeff Bezos doesn't need your money, and it's $75 on Amazon. So please get a free copy of that. I'm also writing for Fivetran, the definitive guide to data transformation. You'll see some early releases of that coming here shortly. Watch for some free codes there. I'm also writing the definitive guide to AI-ready data for Wiley. Also, I'll drop some free codes for that. So a little bit about me. So I'm currently at Fivetran. My only KPI is don't get fired. So far, I'm on track. Shout out Fivetran. This is recorded, so we're going to say nice things. I joined Fivetran as part of an acquisition from Tobiko, where I led developer relations there. We're the creators and maintainers of SQL Mesh and SQL Glot. If you've heard of those open source projects, that's us. Before that, I was the field chief data officer at Dremio. But before that, I had a real job where I used to lead data teams. So I led a bunch of AI and stuff at JP Morgan, blah, blah, blah. And they say those who can't do, teach. And I teach a lot. So I'm a grad professor of data science at a bunch of different places. But none of that matters because I just got my silver play button on YouTube. So now I'm an influencer. None of this matters. So you'll see me making TikToks now for the rest of my income. Just a little bit about Fivetran. I thought I probably should talk about it since we're in the the belly of the beast. So Fivetran can get data from anywhere and put it anywhere. That's what Fivetran is. Super helpful for AI, as we'll look a little bit. And we're all in on data lakes, particularly Apache Iceberg, because of the interoperability that it offers. All right, enough about that. So how long are the talks? 20 minutes? Oh, okay, 20 minutes with 10 minutes Q&A, and Victor can answer that. I'm sure he would love to. So it's helpful before we just jump right into AI and start talking about, oh, here's AI, here's the architecture you need, to think about like, what even is AI? What role does it play in business outcomes? And then why are organizations having a challenge with implementing AI? And looking at the history of data storage and how we got into the mess that a lot of us are in. So when I consult on AI, a lot of times you start asking questions of like, what do you actually want to accomplish? Like, oh, my board says I have to do AI. Great. What do you actually want to accomplish? Right? So, oh, well, we want to put AI in Salesforce. Great. Why? Oh, we actually want our salespeople to be more productive and not have to spend 70% of their time researching or whatever it is. So you start with the business outcome, and then you work backwards to the specific AI capability. And in my opinion, feel free to, message me on LinkedIn later and tell me you don't agree, and I'm sure you're right. But there's 4 general AI capabilities. The first of which is deep learning. And I put that at the bottom because deep learning can really work on raw data. I'm talking recurrent neural networks, convolutional neural networks. Don't come at me. I know transformers are deep learning. They'll come later. But these are RNNs, CNNs. They can work on raw data. A little bit above that, now we've got classical machine learning, analytics. This really kind of needs normalized data. So can't really work on raw, it needs to be normalized. This is kind of what's in your warehouse, your data mart. But now we've got these other 2. We've got generative AI. Now what we should have been doing here really matters because we have to put context on top of it, which can come in 2 forms, either as embeddings, where you can do a probabilistic vector search and find some stuff on your unstructured strings, or through like a semantic search, where on top of your data, you can put meaning and it can do text to SQL, whatever you want. But we have to provide some kind of context for generative AI. If we haven't done the work here or here, this is a problem. And now, even beyond, now we've got agents. Oh, shoot. Well, what's an agent? Well, it's generative AI, but we give it tools and autonomy. Oh, good. So I'm glad we didn't do the work here. Now we're going to give it tools and autonomy, and we wonder why it doesn't work. So why isn't it working, and what are, that was close. Could have been bad. Good thing tech support's here, though. They got us. So we think through, okay, conceptually, we know that this is a challenge for enterprises, but how did we get here? So it's helpful to think through the history of data storage. And if you come at me and you're like, hey, what about like Sumerian tablets? You can leave. Take a beer, but you can leave. We're starting in like the 50s with really we can write to disk. Okay, we got the big bulky machines in 1956. That's kind of like the history of modern data storage. So the 50s, 60s, we start getting these physical databases, right? So they're on-prem, they're difficult to work with, but at least we have something. They've got row-based data sitting inside them, which is awesome for transactions because it can be ACID compliant. It can be super fast because it's just row record level. Awesome. And for the sole purpose of powering applications. So we're just doing writes here. We're not reading, we're just writing. That's it. And if we want to spin up a new app, we really need a new database. So there's a lot of infrastructure overhead. And not only that, if there's tables inside these databases, they don't talk to each other. And that's a little bit of a problem. So not only is it difficult to work with, it's on-prem, it's doing its job. It's writing, it's powering business critical applications. And then this is the way it continues until the 70s. So in 1972, E.F. Codd writes his paper about relational databases. I'm pointing like there's something there. There's not. There will be. So he's saying, hey, we got these data tables inside these databases. What if, crazy idea, we could relate them to each other using this thing called keys? If you're like, awesome idea. So let's keep literally everything else the same. We've got our physical databases, but now we can do a little bit of data modeling. We can normalize the data, deduplicate, right? still row level or record level, row based. I'm saying row level, it's row based, and it's powering applications. And if you need to spin up a new application, you're building a new database. And it's not SQL that we're working with. So it's a little bit difficult to work with, but hey, it's working and it's getting a little bit more efficient because now we can do the data modeling and normalization. So we're making some strides. And this is really what things look like until the 80s, where IBM and then Bill Inman start thinking about, hey, man, Bill's a hippie in my mind. He lives in Colorado. He probably is a hippie. He's like, hey, man, we got all these data silos. What if we could put them in one spot, a single source of truth? Let's see how that worked out. You know, spoiler alert, it didn't. But he's like, hey, what if we could put this data that we're writing in one spot and do this new crazy thing where we read it and then suddenly we can do analytics. Oh, I thought I heard a comment where you're like, boo. And I was like, oh yeah, I get it. I also would boo. Like, boo, warehouses. So we have to get it in there too. So this same time, Bill also helps create ETL that we know and love, right? Extract, transfer, load the data from these disparate sources into one place. Awesome. And now we've normalized, and often in a warehouse, we're going to denormalize. We're going to take it from multiple tables, right? We're going to put it into one big table, keep our analysts happy. Hooray. But in this warehouse at this time, still on-prem, still row-based. So even though we're starting to collect more and more data, aggregating it's a problem because when you do a row-based query, you have to read every single row. So then if you're trying to do a lot of historical data, as you typically do with analytics, super slow. But hey, better than nothing. And they have to do this process overnight because what's business critical? It's not analytics. It's these applications. So they're like, hey, do your weird ETL thing, do your alphabet soup overnight. Don't screw with our applications. And then hopefully it ran. And then you can read it. And you can read from this warehouse. Don't touch any of the databases when they're up and running live. Awesome. So super slow, but at least it's something. But what happened? So this idea of single source of truth, it's an idea, but then different business units see, oh, wouldn't it be cool if we had our single source of truth? So then sales is like, hey, we want our own single source of truth. And then marketing, not to be outdone by sales, is like, we want our single source of truth. If I could spell, everybody's life would be easier. So now we've got all these ETL jobs going on into all these disparate warehouses, right? No single source of truth, multiple silos. And now if you've worked in data longer than 5 minutes, you're like, yeah, it's kind of still like that. Yeah, then this is why. And so in the 90s, Ralph Kimball's like, hey, man, he also is a hippie. I've never met him, but he probably is a hippie. It was the 90s. He's like, hey, we've got all these warehouses and we're pretending like there's a single source of truth and there's not. Let's just admit that there's not a single source of truth and let's create these things called data marts, which are really business unit specific. So he's like, hey, we're specifically just going to, off of these warehouses, we're just going to create our little data marts. And this is HR's source of truth. And this is sales source of truth. And we're not going to pretend like we have an enterprise view like Bill was trying to do with the warehouse. Ralph Kimball's like, dude, we're not going to. So let's just not even try. So we've got all these little data marts, which are more use case specific. Still, storage and compute coupled together, right? You want more storage? You got to build more compute. You need more compute, you need more storage. So inherently you're over provisioning one or the other. That's just how it is. Still row-based. So as you're aggregating more data, it actually did work out more in Ralph Kimball's favor because he's like, hey, smaller subsets of data so that we're not trying to deal with this monster and then trying to do row-based queries on top of this giant historical data. All still on-prem. And these are all still just rows and columns, right? This is all tabular data, which is great until, spoiler alert, we've got this new thing called the internet. And not everything in the internet was rows and columns. Now we've got all this unstructured data. This is going to be a problem. I'm going to pull this off for sure. So currently we're still on-prem, storing tabular data, and we're just expanding, if you notice that. Did they get rid of their databases? Probably not. Maybe they swapped them out for relational databases, but more than likely they just kept adding. So now we've got databases, we've got relational databases, we have warehouses, and we have marts. So far, we haven't taken anything away. We're just continuing to expand our enterprise data landscape. You should be impressed that I just rattled that off super fast. Enterprise data landscape. And now we've got unstructured data, which we're not prepared to deal with. So now we've got unstructured data. We've got, images, videos, all this junk on the internet. So in 2006, there's two different approaches trying to deal with all this unstructured data. You've got Hadoop, boo, in 2006, which comes out with HDFS for the storage, and it's like a distributed file-based system where they're like, okay, let's take this semi-structured, unstructured data file system. We're going to use this awful thing called MapReduce to try to query it. And we're going to have these weird things called Hive and Pig, and you're going to be like, oh, do I work in a zoo? And they're like, yeah, meet Zookeeper. And so we've got Hadoop, which is great. It's actually a very thoughtful concept. Poor implementation, and that's armchair quarterback, watching the Super Bowl, like, boo, you guys suck. So yes, Hadoop did great things for us. About the same time, 2006, 2007, Amazon came up with a different concept. They came up with S3, right? Web first. And S3 is important because what does that do? It separates storage from compute, because they're like, okay, we've got these data lakes. This is S3. You can compliment me on my awesome drawings later. Me and my 4-year-old have an argument about who's better. It's kind of a tie. So S3 is like, hey, we're just storage, and we're going to make our buckets, right, our data available by API. Awesome. So big deal here. One, we can move stuff to the cloud now. Instead of spinning up your own infrastructure, you can just click a manage service button and spin it up on Jeff Bezos' computer and pay as you go. Awesome. So we get rid of a lot of the infrastructure friction. Sick. And we separate storage and compute. Big deal. Because if you need more storage, you're just spinning up storage. If you need more compute, you can just spin up compute. That's a big deal. So, and S3 won. I think it's fair to say that, yes, Hadoop it did its thing. I don't think anybody's spinning up new Hadoop clusters. Lots of people are adding more S3 tables, S3 vector tables. And by the way, S3 is all in on Iceberg. Yay. So, did we take anything away? No. Now we just added a new component. Now we've got a data lake where we're going to dump all our crap. We've got our marts, we've got our warehouses, and we've got our relational databases. And we're like, oh, storage is cheap, so we'll just put whatever we want inside here. And we did. And data lakes don't have all the strong benefits that we had prior with ACID compliance, all of these things. So transaction security, durability, it's kind of like throw it in here. It's eventually consistent. It's really focused more on accessibility rather than like durability. So there's definitely some governance challenges with data lakes, and which is why we still kept our warehouses, our marts, and our relational databases, and we just keep growing. And if you think to like any enterprise ever that's been around longer than like 15 years, this is what their data looks like, right? We've got all this crap that's just grown over the years, and this is powering applications, and we have multiple we have Snowflake and Databricks and Redshift and a bunch of marts powering business unit specific initiatives, and we've got a data lake that nobody except the machine learning engineers use because they can use the raw files to train deep learning models. And this is what Netflix and Uber and Databricks were struggling with in like 2015, 2016, when Apache Iceberg, yay, this is an Iceberg meetup, Apache Hudi and Delta Lake all came out at the same time, where their idea is, hey, we've got all of this stuff going on, and we've got so much data sitting in S3 in our data lake, but we can't really use it because I delete a column and maybe it's deleted, but maybe it's not deleted, and I have to go back to the warehouse anyway, and it's super expensive and it's difficult to use, and there's vendor lock-in potentially. So their idea is, hey, we have all this stuff. we have all these files sitting in our data lake. What if we could treat those files as tables and just abstract away the fact that these are files and just let everybody who needs to use them see them as tables? And let's give them all the characteristics and durability that we love about the warehouse, but keep all the flexibility that we love about the data lake with separate storage and compute, elastic scaling. Awesome. But try to get rid of the governance nightmares. Crazy idea. And that's where open table formats come in. So open table formats like Apache Iceberg organize the data using metadata trees, at least in Iceberg's case, of files so that it abstracts away the complexity of individual files and you just see a table. Because the table is kind of like the atomic unit of working with data. You're not usually going in and dealing with individual files. You're usually working with a table. And why I love Apache Iceberg is because for the first time in a long time, it can start consolidating a lot of this data sprawl. You can now take the data from your marts and your warehouses, and you can keep it in your lake, and you can treat it as a warehouse. So it helps centralize closer to a single source of truth. It gives you that governance. It makes it cheaper because storage is cheaper. It becomes your data because it's not tied up in a warehouse that you can't, if you need to migrate from one to another, it's a nightmare. But if you've got it in your lake and tools can just be interoperable with your lake, if you want to swap out a tool, awesome. You don't have to move it because it's in your lake and tools are just compatible with it through the open table format, like Apache Iceberg. So we begged people to come and listen about Apache Iceberg for years, and nobody cared because they weren't really sure which open table format really was going to last, because Delta Lake, super popular, Databricks land, great. Apache Hudi, great for transactional use cases. Might have 5 minutes. Is that what the cough was? Get off the stage. Like, okay, fair enough. Victor would love to answer your questions. Again, remember, I'm the opener. It only gets better from here. So like even 2 years ago, I helped start the Seattle and the San Francisco Iceberg meetups, and we begged people to come, and nobody came except Snowflake. Shout out Snowflake, because it was at their office and they had to come. So, and this was even pre-Danica. But now, even just a couple months ago, there was a San Francisco Iceberg meetup, hundreds of people. They had to get an exception from Apache in order to hold it. Just everybody wanted to come. Now when we hold these Iceberg meetups across the world, hundreds of people want to get involved, and tons of vendors. What's the change? Well, Databricks bought the company that helped create Apache Iceberg, and they have stated that they would like Databricks to be completely interoperable with Apache Iceberg. So now instead of worrying like, oh, I don't want to choose the wrong one and it'll be a nightmare to unwind it, well, Databricks, the creators of Delta Lake, have said Iceberg's good. So now everybody's like, oh, okay, we can finally solidify on one thing, Iceberg, and make it interoperable. But now we've got AI. Uh-oh. So we were dealing with all this stuff, and now all of our boards are saying, hey, guys, we know that this is what our data looks like. Do AI. So, and they're like, why can't you do AI? Well, there's a few reasons. One, you see the data sprawl. And a lot of people haven't even implemented Iceberg yet. But here's why I'm excited about Iceberg and a role it can play with agents. So traditionally, let's say that you're not doing Iceberg. What would you have to do to meet these different AI capabilities? Okay, deep learning, raw data, where does that live? Data lake. Machine learning, normalized data, same with analytics. Where does that live? That's going to live in like a warehouse. Somebody sleeping? Oh, no, I thought, anyway, sorry. Anyway, it's somebody at home streaming. They're sleeping. Okay, generative AI. What does that need? So now we need contextual data, either through embeddings or through a semantic layer, or both, more likely. Where's that going to live? That can live a few different places. It's probably going to live in a semantic layer, or it's going to live in a vector database. And now we've got an agent. what does that need? That needs operational data. So it's interactive. And it's transactional. So that really needs to live in something like OLTP, Postgres. And why is this a challenge? Well, if you think through, where am I at on time, Victor? Okay. If you think through how we traditionally separate what kind of data we put where, if you look at like the data value continuum, I don't think I made this up. So if you've got individual records, and then you've got like aggregated big data, ag. There's different use cases when these thrive. So like individual records crush it at interactivity, right? One transaction in, one transaction out, super fast, low latency, ACID compliant, perfect, interactive. Both of them can do like small analytics right in the middle. So like aggregate records, individual records. So think like column-based and row-based. So right here, you could do like small analytics. But if you want to do like machine learning or even train a model or fine tune a model, you really need a lot of data. So that's really going to be more the aggregate. So this is really kind of like row-based, OLTP. Yes, there's hybrids like ClickHouse and whatnot. So, but in general. And then this is like columnar, like Parquet, OLAP, which is fine because we could do like Postgres, we could do like a warehouse and a data lake. We could kind of separate them. But the challenge is AI, especially AI agents, need all of it. So how are you going to do that? Because you're interacting with it and you need that operational transactional data to move very quick, low latency, but you also needed to have access to your columnar data. You needed to have access to an enormous amount of data, but it needs to be structured and contextual. So how are you going to balance that? Well, here's what I'm seeing in the wild, is that Iceberg is not a transactional database. You still need a Postgres. You know, we saw, what company do you work for again? I'm just kidding. We saw Snowflake acquire Crunchy Data, right? We saw Databricks acquire Neon. Postgres is crushing it everywhere. Why? Because it's transactional and it really supports that operational data that agents need, managing memory, managing policies, APIs, how many turns should it remember, blah, 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 all that fun stuff. So you're going to have some kind of OLTP, Postgres. But then for all these other things, if you're doing the analytics, the ML, if we're still in this sprawl, like a lot of organizations are, they're like, oh, crap, we've got 40 warehouses and 50 marts, and oh, we've got a data lake there too, and we don't really know how to combine it and give our agent access to it in a secure, repeatable, efficient way. Well, that's where Iceberg comes in, where, again, you can do your deep learning on the data lake. You can do your analytics, your machine learning, and your fine tuning on the Iceberg. So then it drops you down to more like 2 components, potentially a third if you're going to do embeddings and you're going to put that in a vector database for your, unstructured strings that you need to do. But what's working is that like just the operational data can live in Postgres, low latency, super fast, but everything else can really live in Iceberg, and we can get much closer to that single source of truth. So getting into Iceberg can be a nightmare, potentially, if you don't do it right. Shout out 5tran, makes it super easy. Where's marketing at? Okay, I get to keep my job. Remember my 1 KPI, don't get fired. So this is helping me. So this is where Iceberg plugs into AI and agents, right? Does it drive everything? No. But does it help simplify the data landscape so that you can start getting closer to a governed, secure, more efficient way of doing AI? Yes. Pairing it thoughtfully with the other components that you may need, whether it's Postgres, maybe a vector DB, but you can do all of your columnar queries and needs directly on your data lake, super cheap. Swap out your tools, right? All that interoperability through Iceberg. So that's what I'm seeing work out in the wild. I have a demo if you want to see it afterwards. Look, I actually make slides. I'm just showing you this for proof that at one point I made slides. But boop. So if you want to do any of this for free, I've got a tutorial here to completely do this stuff for free. Ping me on LinkedIn if you want to see a tutorial of how to build an agent on top of Iceberg and then using like DuckDB as the transactional database. Happy to show you that. Thank you so much. Okay.
Thank you, Andrew.
What questions would you like Victor to answer?
Go ahead. Any questions, guys?
How do I have a job? I'm a personality hire, as Danica likes to remind me. So that's question number one. We've worked together at 3 different companies.
All right.
Awesome.
Thank you very much. And guys, in a network break, you can ask any question about agents in Iceberg. Thank you, Andrew. Thank you.
Thanks, everyone. Okay. Oh, I didn't send you the StreamYard link. What is your email? Are you in the Iceberg Slack?
No, I'm not.
Okay. If you give me your email, I'll send you the link real quick to.
Nico, what?
Are you online?
I need to put it in the other computer. Yes.
Lazar.is. You can, or one.
Okay. I will get you up there shortly. Oh.
Stage is yours.
Hello, I'm Nicoletta. I come from London, where I work for a company called Fresha. I will have a slide at the end about that, but today I want to talk about query federation to Apache Iceberg using Starox. Now, there are a couple of words in that title, and I'm curious to hear at least how many of you have heard about what federation is and what Starox is. Okay, 2, 3 people. Okay, that's yay. Okay, so on today's agenda, we will touch a little bit on what query federation is, the two philosophies of how you can think of or how query engines implement it, and then we will dive directly into how query engines such as Starox interact with Iceberg, and they can actually federate to Iceberg. We will learn how an example of how metadata is navigated, how data files, how we can deal with deletes, and we'll see what we can learn from all of that. But I want to start somehow from the end to understand why federating and why Iceberg is very important in data architectures in general. So I will start with a question. So when you are asked to build analytical systems and in general reports and analytics, what is the number one requirement that usually the PM or stakeholders ask you to do?
No vendor lock.
Okay, that's a good one, yes. So no vendor lock. Anybody else? Faster queries, exactly, and real time, right? Reports need to be real time as possible. I get my, I don't know, new transaction. Now it appears in the analytical report, right? And that is quite complicated to do. Now, of course, real-time analytics can be done in various ways, but if we don't want vendor locking, we need what is called, I don't know if this thing, yeah, it doesn't work to show with this pointer, but we need a data lake, right? We need to ensure that we are not, if we don't want to be locked in a warehouse, right, behind an internal format that is not universal and is not reusable, then we need some sort of a data lake, and we need to essentially separate cloud and compute and ensure that we have these open table formats, which can be anything. In our case, we chose Iceberg. And then we keep in the data lake all our historical data. But what about the real-time data? How about this data that gets ingested right now, right? We need, if we could ingest it in real time in the data lake, however, that's quite expensive at the moment, right? Even in Iceberg as well, it is quite expensive, and you are limited to the table maintenance that you need to do all the time if you don't want to get many small files on the system, right? In S3. So you technically need a system that is able to put this real-time data and then have a query engine that allows you to federate against those two systems. So essentially, you want to be able to have a unified SQL access across your data architecture, right? And this is a way of building a unified analytical architecture. Now, if you can bring in other, like in here, if you can bring from all over other sync lanes, any sync, if you can bring it in your architecture and treat your data, be able to unify it, it's even better, right? So you can add as many sources as possible, for example. So what is query federation, right? It's just this idea of giving you a unified SQL access such that you can query your data without needing to move it, without putting into a single big warehouse, and without copying and having n copies of the data, right? Which normally is very difficult to keep in sync, right? This allows essentially to simplify data architectures quite heavily. Now, when it comes to federation, technically there are two ways, right? Or paradigms, philosophies, I call them in here. Now, you can say, I have an engine The engine knows how to orchestrate across sources, but that's pretty much all it can do, right? So this is this idea of tree, now where you have many sources, you can have you handle any number of you can connect to any number of databases, and the idea is that the data is queried in the source external system, right? And in this word, federation is mostly just an SQL orchestrator, not much more than that, right? But at the same time, there are new OLAP engines that want to give people access to external data and bring it internally as if it is internal data, right? So to make it transparent for users and to not care where the data comes, where it is actually saved and stored. And in that case, you don't want to handle everything. Most of these engines actually specialize on a couple of use cases and sources that are used all the time in the industry. So for example, data lakes, Postgres and relational databases, maybe Elasticsearch for search, but not everything under the sun. Yes, in this case, you optimize for predictability. Now, there are some challenges in here because nothing comes for free. And if you have many data sources, it's very difficult to essentially predict how it's going to perform, right? You are normally dependent on the slowest source. And then people, like the query engines, need to also account for network policies, for access patterns, right? To have this unified SQL access, right? But what is even more challenging, it's actually querying these data lakes, right? Because ultimately, they are just files somewhere in the cloud, right? So if you really want to query and make sense of the data within a data lake, there is a lot of load or semantic load that these engine need to understand, right? So these engines, the SQL engines need to know how to interpret all the metadata that's put on top of those files. They need to know and understand the statistics of each table. They need to know how to navigate those file trees, right? And in some cases, and of course, there is latency associated with querying S3, which this is quite obvious. Now, as the data lake as new data gets ingested into the lake, there is this problem of file fragmentation that, the engines need to somehow overcome, right? And of course, schema evolution is challenging in any sort of data architecture, not just in data lakes. Now, I mentioned Starox, and only 3 or 4 hands were now. Yes, okay. Now, a couple of words about Starox, because all the examples will be about Starox. And why Starox, right? So it's an OLAP database, right? It is built on top of Apache Doris. It's open source. And what is special about it? Well, special. It has this vectorized MPP processing engine, right? For us at my company, we decided to use it because it is compatible with MySQL. So introducing it into the ecosystem felt very natural and very easy to do, right? But Starox is actually a federated query engine and has a lot of lakehouse integrations, not just against to Iceberg, but also other data open table formats, right? But with Iceberg, they actually invest quite heavily because a lot of their customers use Iceberg. Now, we want to learn how Starox actually queries Iceberg and what techniques it uses to optimize. So we need a recap of how actually Iceberg stores the data, right? And how it separates the metadata from the actual data files, right? So in order to navigate and to read these data files from S3, you need actually to have access to a catalog and then scan metadata files, manifest lists, and manifest files up until you reach the actual low-level data files, right? Now, again, the same idea. If you want to read from Iceberg, you either can read directly from S3, which is fine, but you'll have to pay the price of scanning files all the time, or you use a smarter engine that actually says, okay, I will retrieve once, cache the metadata, cache the results, and potentially allow even to build materialized views on top of these Iceberg tables such that I can reuse a lot of the calculations. In Starox, in fact, which employs a lot of optimizations for minimizing the remote reads, right? This is the idea, because they want to be as cost-effective as possible. So I have here a diagram. Now, in most of these, like all databases, right, there is a separation in between the front-end nodes, or the coordinator, the query planning, query analyzing, query parser, and the actual compute layer, or compute nodes, backend nodes in other databases, right? So when a user does a query, that query will be sent over to a front-end node, right, to a coordinator. And the coordinator will start analyzing the query, right, and plan it, right? In the case of Iceberg, it has identifies the table name, goes to the catalog, right, because in Iceberg you need a catalog, which can be anything. In our example is Lakekeeper, which we use heavily. And from the, as the catalog where the metadata is, right? And then from there, actually, the front-end nodes need to retrieve all the manifest list, manifest files in order to then be able to plan the query and send that plan to across multiple compute nodes to be able to actually, in the end, read only what is necessary, but not more than is necessary for a query. So now let's take them one by one, because this is quite important. Navigating metadata, right? Now, I showed earlier the tree, right? In Starox, in order to reach to the manifest list, right, you need essentially to read them, right? Now, you don't want to read everything, and what Starox is doing very well is to decide based on the query and the number of metadata manifest lists that it needs to read, how to do it, right? It has this algorithm, which is called adaptive retrieval strategy, that essentially is used to say, okay, is it okay for a single node to read all my data, or I need to somehow split the reads into across multiple of these compute nodes, such that I can do a lot more work in parallel. And once the metadata is retrieved, it will be put in cache. Next time around, no more scanning of these files, right? Now, I have the manifest lists, right, which I retrieved the previous step. Yeah. How do I actually get to the files? And now I think most of us are familiar with this idea of pruning, right? This idea of, okay, I have some files, but I need to read some files, but maybe I can identify before reading what I can skip and not read at all, right? And technically this is what Starox is doing, and I guess most of the query engines. However, Starox seems to be doing it a lot better than others. Now, so there are two phases, right? On one hand, we need to prune as much as possible from the metadata and manifest files. And then we want to scan as little as possible from the actual data files, right? So the very first thing that we need to do is to apply partition pruning, right? When a query has, when the table is partitioned and the query only includes 2 partitions, I only want to scan those and files about those partitions. And then with whatever files remain, Starox applies even more pruning based on statistics on different columns, right? Because not all columns would be in the partition specification, right? Once these are filtered, then it gets into the actual scanning and the actual planning of the query, such that in the end, it pushes down the predicates up to the storage layer, right? And this is how Starox ensures that if a column is not needed, it will not be used, right? In the end, the actual data will be returned. Now, data files, in some cases, right? Iceberg has the concept and handles deletes, right? I'm not sure how like familiar is everybody with the concept of deletion files and the two types of deletion files, but the problem with them is that they need to be applied, like the logic of handling deletes needs to be applied on the fly, right? Some of the query engines handle only positional deletes, but not equality deletes, or vice versa, because actually handling this type of files is quite challenging in query engines, right? And we had issues with equality deletes many times. Now, how does this actually work? It's very easy. When if we zoom in just on reading the data files, right? If there are delete files associated with that, we just determine. In the case of positional deletes, we filter just by path and the row index. If there are equality deletes, of course, we need to identify the rows, the keys, right? To filter by the keys in the records themselves, right? But once this processing is finishing, that's when the filtered rows get returned. We actually looked into the source code, and there is an article about all of this. I will share at the end. Now, so as a recap, Starox will optimize federating to Iceberg based on many strategies, but most important, aggressive partition pruning, data skipping just based on statistics from all the columns that comprise like any filter in the query, predicates pushdown into the storage layer, and caching metadata. Yeah. How it looks in practice, right? So I have here an example. The query is very simple. It is a view. But underneath that view, it's actually a join in between an internal table in Starox and in an Iceberg table from the data lake, right? What is interesting, I don't know if it's visible, but there are like 9.7K records to be retrieved, and the Iceberg scan ends in like 2 milliseconds, 1.97. So it is quite fast. Underneath that view, there are other joins, and this graph I generated with just dbt docs, essentially. So it's just the joins underneath those. Now, I was mentioning earlier the challenges of querying data lakes, and let's see how we kind of solve those, or how Starox addresses some of those challenges, right? So, of course, for object storage latency, caching data and metadata helps overcoming the problem of going to S3 all the time. Data freshness can be solved, as I was showed in the first slide, right? By separating the data in between the historical and the new and fresh data, and then federating across those within a single system with a unified SQL access. File fragmentation and the problem of table maintenance, right? If you just cache the metadata and then you build materialized views on top of the Iceberg table that you don't need to go to S3 as often, right? So we are less, table maintenance is less problematic. And schema evolution is assured by default in Starox just because it has these tasks in the background that refreshes metadata all the time, right? So it comes for free, essentially. Well, not for free, but transparent for us. So now, if we think about this idea of data lakes and querying them and federating and the idea of unified analytical systems, well, the industry does shift towards cheap, reusable, and universal storage, and most companies do not want to be vendor locked in anymore. That's why companies like Databricks and Snowflake, they do invest heavily into Iceberg and open table formats in general, right? And query engines themselves need to adapt to these new lakehouse architectures, right? Starox is just one of the many, right? It's not the only one, it's one of the many that invest quite heavily into these lakehouse integrations, and including Apache Iceberg. And the integration is quite well thought. And I think this is it. If there are questions, I'm happy to give more details about the first diagram from the beginning and how we actually implemented some of the concepts. I'm Nicoletta, and in there is a link to a Medium. We have a blog at the company called Fresha. And we actually document all our journey there, including all these like why Starox, how federating to Iceberg works, how Starox handles merge and read versus copy and write in Iceberg and so on. Right. So yeah.
Okay. Nicoletta, thank you very much. Starting from the end, like a Sherlock Holmes from a crime scene to understand what happened. Any questions, guys, about Starox, Iceberg, usage, and pressure? If not, so what we have right now is a 20-minute break, so you can just grab a drink and digest what was said. And there is a person about the IT archaeology. Probably that was the title. So just to dive in to see what was like the cause. So feel free to use the next 20 minutes to use for
Yeah.
you.
I have a question.
Okay.
Oh.
Are you using Starox open source or are you using self?
Open source.
Oh, okay.
Yes, open source. Everything we built on open source. Like we didn't want to be vendor locked in,
Yeah,
right?
They have like the
Yeah, they have seller
fundamental
data.
material I can use.
Yeah. They have seller data, but we don't use that.
Okay.
It
Very cool.
also felt very expensive when we looked, so no.
Perfect. Guys, 20 minutes break.
Thank you. Okay.
So we have our third speaker, Danica from Snowflake, talking about.
In case you didn't know, I was from Snowflake. In case Andrew didn't say it enough times. Sorry, I took that from you. All right, everyone. I am horrifically jet lagged. And so to make up for that, I am going to be the most excitable speaker you've ever met, which is really hard to beat on Andrew. Did you get the beginning of that, Andrew, or just that end of the mic? Fantastic. I love that. So this talk is iced coffee because I like to have fun with my talks. Otherwise, nobody has fun. So here we are. So when I was putting this together, first of all, for some context, obviously I work for Snowflake. When I originally started working there, I was exclusively focusing on Iceberg and Polaris. Now I run all their open source DevRel stuff. So I get the freedom to talk about whatever fun technologies I want to. In the past, I used to advocate for Apache Kafka. Hence why this thing happened. So Kafka and Iceberg, this is a common two technologies to put together in one architecture. We'll get into that. But the title is kind of born out of that because we have Iceberg, we have coffee, so iced coffee. The Germans sometimes laugh at it. Not always. What? No, I'm going to hold it, man. Get out of here. This is way more fun. What do you mean?
We have everything. It's up to you.
I'm not that much. Well, now it's here. Like if I don't use it, you're going to be like, well, Danica, she's such a diva. We were going to have fun. Okay. Anyway, can you use, I guess, whatever. All right. So we're going to talk about what your options are for moving data out of Kafka into Iceberg. I know we've kind of touched on a lot of these things to a degree over the course of the last two talks, but I'm going to re-level set on all of them. How many of you are using Kafka right now? How many of you have at least heard of Kafka? Could all of you, if I corner you, tell me exactly what Kafka is? Great. So for you, so Kafka is a distributed event streaming platform. In Kafka, events are produced to and stored in individual partitions of a data set called a Kafka topic. You follow? Great, fantastic. And these events are ordered by their timestamps. Once they're stored in that partition, in that topic, any downstream consumers can come and consume that data in order without impacting the other consumers. Great? Got it? So basically, Kafka lets us build this distributed pub subsystem. Fantastic. But it also allows you to build out an architecture that takes advantage of the fact that there's probably going to be multiple partitions in that one data set, that one Kafka topic, right? And so in that case, you can build out consuming applications that consist of a number of consumers and have them work together to parallelize the processing of that data from that topic. Great. We'll quiz you later. OK. So fantastic. Everybody loves Kafka, right? Yes. Kafka's the best. Oh, and I forgot. I have stickers for you all, and they're shiny. Okay, they're shiny Kafka stickers. I saved them for all of you. Okay, so Kafka, a lot of people are using it because we want to do real time, right? Everybody wants to do real time, except when they don't want to, and that's kind of when Iceberg might come in or be a little bit more relevant. But no, really, when we think about Kafka going into Iceberg, the reality is that you don't always need your data to be in Kafka, to be streamable, to be real time forever, right? A lot of data has a time to live. And beyond that, a lot of teams want to offboard it to something cheaper so they can you still use it for analytics in some other way, but it doesn't necessarily need to be in Kafka forever. Okay, so Iceberg is something that we plug in to store that data. Cold storage, right? So anyway. So we all know what Iceberg is at this point. I'm not going to go over it too much, except that I do want to add a little bit of flavor here because I think that Iceberg is the love child of data warehouses and data lakes. I don't think anybody said data lakehouse tonight, did they? Yeah, missed opportunity. It's crazy. I'm the third talk of the night at an Iceberg meetup, and I'm the first person to say lakehouse, and I don't even work for Databricks. Okay. So one thing that I want to call out when we think about Iceberg, because how many of you are new to Iceberg tonight? Man, you just showed up for the pizza. I'm glad that you stuck around. This is great. So again, for you specifically, when we think about Iceberg and we compare it to the other Sumerian tablets and other ways that we store data, you think of just like spinning up a database, wonderful, but Iceberg is a bunch of files, right? So I don't want you to think about, and I know we're talking about moving data from Kafka into Iceberg, but you really need to think about the structure of Iceberg because it will inform how you actually make decisions down the line, okay? So this is my segue into what Iceberg looks like. Wonderful, isn't it so shiny and beautiful? Iceberg is not a database. It's not a thing you spin up. Iceberg is the format. Iceberg itself, when we say Iceberg, defines really what this layer of metadata looks like and how it should be formatted and how it's all connected and what the pointers look like and stuff. So the way, I don't want to bore you, but we'll make it fun, I guess. So we have our data files here all the way over on the right. These are the rows in our Iceberg table, but it's also deletion files, and we'll get into those more. I'm glad you brought them up because they're really important, okay? So we have all of our data files. We need to track them with some sort of metadata. So we're going to start off with our manifest file. Manifest files are going to point to some subset of data files in a single Iceberg table. Okay, we are going to keep track of some statistics within that manifest file. So they know what their data files that they're responsible for look like. Okay, they know specifically the max and min of the data within each of those columns. Okay, that rolls up to a manifest list, which is exactly what it sounds like, a list of manifest files, except that we're taking a lot of the statistics from that manifest file and we're going to roll it up to the manifest list and basically aggregate that into, per partition, what does the max and min of the columns actually look like there. Okay, and importantly, the manifest list points to all the manifest files within a specific snapshot of that table as it's evolved over time. And then we ran out of good names for files in the metadata layer, so we called this one the metadata file. Yeah, and so it keeps track of all of these snapshots again as it's evolved over time, and we have pointers out to the relevant manifest lists for that, so you can trace it down this metadata chain. The metadata file also has metadata, like the partitioning spec, the schema as it's evolved over time, table identifiers, a couple other things thrown in there as well. This is chaos? I don't know. I think it is, right? There's a lot of files that we're throwing around in object storage, okay? And they're all just pointers. None of it relies on a directory structure, okay? Keep that in mind too. And so to maintain some semblance of order, because when we are adding new data files to an Iceberg table, we have to create a new manifest file, a new manifest list, potentially, a new metadata file, right? We're adding a new snapshot to this. And so this can get out of hand pretty quickly, okay? Especially if we have multiple engines interacting with our Iceberg table at the same time. So to help us maintain order here, we have a catalog. And this is also going to help make this feel a little bit more like a database. Okay, so the catalog's job is really simple. It is just here to maintain a mapping between table identifier and the entry point, the most recent metadata file that we actually need so that we can then query the data files. Okay, and all of this is set up so that hopefully when we want to query the data and we have a large data set, we want to be able to query that data as efficiently as possible and not open up files that we don't need to open up. Okay, the catalog also is going to help make sure, resolve any conflicts if we have multiple engines trying to update this table at the same time. Okay, this is stuff that you don't use here. Okay, so when you're using Iceberg, you have a lot of different ways to actually interact with these tables. Because again, Iceberg is just this. Iceberg's not a thing you spin up. And so to actually generate these files and have Iceberg tables, you need to use a compute engine to actually kick that off, okay? I feel like I have you. You are following so well.
Yeah, that makes sense.
Yeah, you sat through the first two talks, so now you're like, yeah, this is what it means. Okay, great. There's a lot of different compute engines that you can be using to interact with Iceberg tables. The most important ones, I think, are the ones that ship with the Iceberg project. Okay, so the Iceberg project, that community maintains implementations of Apache Flink and Apache Spark. So those should be your go-to, I think, if you actually want to interact with Iceberg or get started quickly. But importantly, there are dozens of them. Dozens of other compute engines. Nobody got that reference, right? That's fine. There are so many other compute engines out there that you can use to interact with those same Iceberg tables. Because an important thing about Iceberg, repeat after me, is interoperability. Interoperability, right? So it is crucial that we, and to the benefit of you, to the benefit of the open source project as well, that we have as many of these external engines that can interact with those Iceberg tables out there as possible. Okay, you should want that. You should be fighting for that so that we can avoid vendor lock-in and have choice. We like that. Yeah, so we want that to be great. And this is not all of them, that's fine. Yeah, so with Iceberg, similar to, going back to Kafka, because that's the point of this, right? In Kafka, one of the important things there is that you can write your data to a Kafka topic once and then continue to stream it, continue to use it for many different use cases. It's kind of the same thing in Iceberg, right? We want to write it once to an Iceberg table and then use it for whatever compute engines we want and not have an issue, right? We can swap them out for different things, okay? So they're kind of like the same. I'm not saying they're the same. How do we actually interact with it? This is just for you, man, here, the queries. This is just normal queries, okay? But I do want to go back into deletes. And this is probably too far into the weeds, but we need to know it for this, okay? So in Iceberg, there are two main ways to handle deletions, okay? We have copy on write and merge on read. And you didn't go that far into these, right? Yeah, you set me up. This is great. So in copy on write, if we have 3 rows and we want to delete that 3rd row in that one data file, then we could just rewrite that data file without that 3rd row. When do we do that? On write, hence copy on write, okay? With merge on read, we're going to keep our existing data file exactly as it is. And in order to handle the delete, we're going to add a new delete file into the mix. And there's 2 ways to do this also. The first is by using equality deletes. And so with equality deletes, this can apply to many data files in the Iceberg table at once. And it says that whenever we see an element, when we're looking at, we have to look at the past timestamp, right? Whenever we see an element, a row from a timestamp earlier than when this delete file is written, and it contains this element, espresso in this case, then we are going to delete it. When do we ignore it? On read. Hence, merge on read. We are reconciling that data file with the delete file. So it is on the reader to handle that. This is on the writer, okay? So it's more upfront work, okay? But there are 2 types of deletes in merge on read. We also have a position delete. So it's very similar. The position delete file can apply across multiple data files. But in this case, we get more specific. We are saying, for a given data file, we are going to ignore exactly this element, a 0 index, okay? Okay, now looking at these 2 options, and for you, sir, who has just learned about Kafka and streaming and doing things real time and doing it fast, right? Which do you think is going to be more aligned with real time, with this streaming paradigm? Merge on read, right? Because when we are thinking about Kafka consumers, the application that's actually going to read from the Kafka topic and move it into Iceberg, all it wants to do is process this element as quickly as possible and move on, okay? It doesn't want to be hung up on trying to handle copy on write and rewrite the entire data file. It doesn't want to be waiting, okay? So yes, it's way more aligned to just dump it in. If we have deletions, wonderful, we're going to throw it. We want to be using merge on read. Great. But a kind of annoying thing with delete files is that we're introducing more and more small files into the mix, right? It just has 1 line in it. That kind of sucks. And so by introducing these delete files, we are introducing more and more small files. And in Iceberg file I/O, opening and closing and having to handle all of these small files, that's a performance killer, okay? And the whole point of Iceberg is to be efficient with our queries. And we're kind of throwing a wrench in it when we introduce too many small files. So small files, these aren't just a problem with merge on read mode. It's just a fact of Iceberg. Because when data files are written, they're limited to containing some number of partitions within them, okay? So depending on the granularity of your partitioning space, or just how your data looks, or how that one chunk of data during that one bulk write looked, that's gonna affect how your files look ultimately, and can affect just the number of files that you have in there. And to make things worse, files are immutable. Okay, so we can't go back in time and just add more data to them. Okay, yeah, you get it.
Because I thought, why do we go back and rewrite after? Like if we do merge and read, I was thinking, why eventually don't we modify the original file? But they're immutable.
Oh my goodness, but hold that thought. Okay, what if? What if? So we don't want to have a bunch of small files floating around. We want to consolidate them. Okay. The solution here is to have fewer small files, right? So just do it, okay? There are mechanisms that are built into Iceberg that we can use to try to have fewer small files floating around. We already heard about copy on write. But again, for streaming, we really would rather be doing merge on read. So what are our options then? How do we continue to have efficient Iceberg tables for those few people that are trying to read all of our real-time Kafka data after it's been dumped into Iceberg for very important analytics use cases, okay? So we could try to be smart up front. And I know that we're all developers, we're all very, very lazy. We don't even like to think about schemas up front, which is why we like to evolve them, because whatever. So probably you're not going to choose this option of actually sitting down and thinking about your partitioning space. But ideally, if you have a choice on how you're partitioning your data, you want to choose a narrower partitioning space if you possibly can, because then you force there to be more data per bulk write in a single file if you possibly can, okay? But again, sometimes it's just not going to work that way, okay? And just the reality of how you're actually bulk writing into Iceberg, or maybe you're not bulk writing, right? The reality might be that you'll have small files introduced over time, okay? And we want to be able to cope, right? So thankfully, we have an option to do that with something called compaction. And this is such an important part of Iceberg that we're going to talk about it here. See, I just want to call out, I made all this artwork myself with Google Slides, shape by shape, okay? Yeah, right? Okay. And I also thought it just worked out that it was coffee themed, because look, of course, compaction, right? Okay, great. So the idea with compaction is simple. We are going to read from small files, ideally from the same partition, and we're going to rewrite them into larger files, ideally fewer of them, okay? So we're going to consolidate everything if we can. This ships out of the box with Iceberg through its Spark actions. So specifically when you're using Spark, you have this available to you. It's called rewrite data files. It's fully configurable. You can choose what compaction algorithm you're using. If you want to filter the data first before you actually go ahead and do that. If you want to target specific partitions or specific files, or limit it to certain file sizes or what have you. It's like the world is your oyster. Okay, you decide what the output of this compaction really is. Okay, so you have the ability to consolidate all of that. So this handles our data files, but you might be wondering about delete files. Yes, because that was the whole point of this. What happens when we run compaction with our delete files? Well, compaction operates as a read. And if we have delete files, we are using merge on read, okay? So when compaction runs, it will actually reconcile the deletion files against the data files and write a brand new, beautiful file that's effectively what we have in copy on write, right? That sounds fantastic, and usually it will be that fantastic. I do want to just say, asterisk, that after you run compaction, it is not always a given that that delete file that you were reconciling will be fully irrelevant. Right? It might still apply. You might not be running compaction over the entire table, which is a very common practice, so that you don't take the table offline the entire time. And it might not be the case that all of the rows in that delete file were reconciled against the data that you were compacting. So it might still be there at the end. But you get rid of a lot of other small files, so that's fantastic. Okay. So when you're running compaction, and this is something you will have to do. Okay. You cannot have an Iceberg table and just exist and not do maintenance on it. Over time, you will have to handle it and do some sort of compaction and clean things up, okay? So just calling out the hard reality. Cool, right? Now you know. Yes, the hard reality. So compaction is great. We should totally do that. That's going to take care of our data files. But there were so many other files out there, in the metadata layer especially. I also want to call out that rewriting your manifest files every so often, which is also conveniently built in to Spark Actions, is something that you should probably do as part of regular maintenance. This is your PSA. Great. So now let's talk about Kafka again. You know way too much about Iceberg. So now let's go back to Kafka and streaming and think about what your options are for moving data from Kafka into Iceberg. So when I wrote this, I really wanted to focus on just open source tools specifically. And I had to limit it a little bit. But there are a lot of other ways that you can do this. But I wanted to focus on some of the ones that were most obvious that a lot of people who are encountering this problem space are probably considering first. Okay, so you have Apache Spark, Apache Flink, and Kafka Connect. Every time I write this talk, or not write this talk, but every time I go through this talk and try to update it, I want there to be an obvious winner. I really want there to be an obvious winner. But as we'll see, there, like, it really depends on what your use case is, what your team looks like, what your SLAs are, what you're trying to do. Okay, so I'm going to hopefully give you enough that you feel that you, sir, are confident. When you go back and you start using Kafka and Iceberg for the very first time, you know exactly what you need to do. It's probably going to be Kafka Connect. But anyway, for you, it's obvious. But yeah, so I just want to add that sort of a side note there. Okay. So let's get into it. Oh, I also want to call out that for these three, it's also just interesting that some of these are going to feel like a more natural choice depending on how you're approaching this problem. So if you're approaching this from you and your team maybe are maintaining Iceberg, you're on the analytics side of things, Spark and Flink are going to feel like very obvious options for you because they're first-class citizens in Iceberg. Right? The Iceberg project ships with implementations of these. If you are taking care of your Iceberg tables, you are using Spark, probably, right, to maintain those long-term. So those are going to feel obvious. If you're approaching this from a streaming perspective, like maybe the data lakehouse people were like, hey, could you pretty please move this data into Iceberg for us out of your Kafka cluster? Then Flink and Kafka Connect are going to feel more obvious. Flink, if you're doing some more streaming and stream processing, Kafka Connect, if you want to just stay really close to the Kafka ecosystem in this project. Okay. So now let's dive into a couple of these. So for the Kafka to Spark to Iceberg, again, Spark is effectively a first-class citizen from the perspective of the Iceberg project. Especially with the Spark actions, with all those maintenance tasks that you have built in here. You're going to have to do those eventually if you're focusing on open source solutions when you're working with Iceberg. So when you are building out this pipeline to read data from Kafka, do some processing with Spark, and move it into Iceberg, it's going to save you a couple mental cycles to also have that be in Spark, in addition to maybe how you're interacting with your Iceberg tables and maintaining them. Yeah. So I think it's worth mentioning that if your team is not responsible for maintaining Iceberg, if you're not already working with Spark, maybe don't do it. Okay, maybe don't do it. As far as functionality goes, you've got pretty much everything in here that you might need for moving it into Kafka, and a lot of bells and whistles that you can play around with. One thing I want to call out is that upsert functionality is a little clunky. So if you want that specifically, you can do it. It's just a little clunky. There's also a fun overwrite mode, which for those of you, not you, who have used Kafka, how many of you have used a compact topic? Yeah, you, sir, have used a compact topic. Incredible. So overwrite, I feel like, is only useful there. So what overwrite does is it basically gives you the opportunity to completely rewrite an entire table with a bulk operation. And when I was using compact topics, I feel like I was like refreshing them every so often for any applications. And so it just made sense to like read everything from the compact topic again, flush it into Iceberg, and overwrite that table just to clean it. Fresh start. So, but other than that, Spark, yeah, limitations of Iceberg, upsert, great, perfect. Equality deletes, did you like those? Well, they're trash anyway. You don't need them. So it's fine. Also, when you're looking at Spark from the perspective of streaming, it's not. Okay, I will fight to the death on this. This is the hill I die on. This is fine. So if you are approaching this from the streaming side of things, from real time, this is not Spark. Okay, period, the end. It's micro batching. Okay, but who's counting? So yeah, I mean, this probably doesn't really matter. Honestly, if you're moving your real-time data into Iceberg, you don't really care about how fast it gets into there, but that's neither here nor there. Also, we have something called fast append mode, which will hopefully help. So basically, fast append mode creates the least amount of metadata overhead that it possibly can. The queries might be a little less efficient later on, but you're basically just trying to get it into Iceberg as quickly as possible. Okay, so that's an option too. All right, so for Flink, another win for this solution is that, again, it's kind of a first-class citizen from the project perspective. We have support there, and so what it means is that you can interact natively with your Iceberg tables natively using the built-in or the available Iceberg connector. Okay. So for your Kafka to Flink to Iceberg pipeline, you'll be writing a Flink job with a Kafka source, which is, if you haven't used that, that's probably the most popular Flink source, I think. or very close if it's not officially. You might be doing some sort of stream processing, some transformations in there. The benefit of Flink is that you can actually combine streams pretty easily there because it is actual streaming. Okay, you have flexibility to do that. And then you're going to use the Iceberg sync to actually sync that into your Iceberg tables at the end. One thing I want to call out in case you don't like to use the latest and greatest, there are 2 syncs that you can use. There was the horribly named Flink sync. It was like the Iceberg community was like, no, we are just Iceberg and there are no other syncs. Like Flink has 0 other syncs. So we're going to call it Flink sync. Wonderful. And then there's the newer Iceberg sync. Yes, that's great. How many of you use Flink? Okay. Yeah, like, are you in tech?
No,
Okay, cool.
surprisingly, yes.
Okay, that's fine. You got like, okay. This whole talk's just for you. So I'm so sorry. Yeah, so for those of you who are familiar with Flink, the Iceberg sync was like a rewrite of the original Flink sync that uses the V2 Flink sync abstraction that the entire Flink community was rallying behind for a little while. So it's a lot more robust. With this, we can achieve exactly once. We like that. We really like that. We like that. Yes. Small file compaction, you have a lot more flexibility in configuring that as well. And people have promised me that a lot more inline maintenance tasks are coming with Flink as well. So again, Spark is kind of the golden child from the Iceberg community. Okay, all of the actions that we built in for maintenance and stuff, those are in Spark first, and then occasionally people are like, hey, what if we put that in Flink? So that's coming. So Flink has a lot of nice things going for it as far as moving data, being part of this pipeline here. Also fast append. All of them have it. I keep calling it out because I think it's something worth knowing. Okay, Kafka Connect to Iceberg. How many of you have used Kafka Connect? Not enough. I love Kafka Connect, okay? I think it's pretty cool. I'm just going to wax poetic about just the way this thing was built. So Kafka Connect, this connector specifically uses a centralized coordinator to read in all of the partitions across the connector tasks, holds them for a little bit. So you have flexibility to kind of aggregate the a single write operation and push that into Iceberg. So it can help to mitigate the small files, which is great. It's nice that they added that in there. But again, there is a trade-off between how quickly you're actually consuming from your Kafka topic and holding it as well, okay? In Kafka Connect, we have no built-in maintenance tasks, okay? So if you're introducing small files into Iceberg, someone will have to clean those up. Maybe it's you. It's you. You've just inherited a data lakehouse and you have to take care of it. What are you going to do? Other benefits of Kafka Connect, I think it's just got everything. In my mind, it's perfect. It's really like if you want to get started, you're approaching this from just the Kafka perspective and you want to immediately move things into Iceberg and not think at all, the Kafka connector is going to get you very, very far. Yeah, you might be able to do stream processing in Flink, but you've got single message transforms in Kafka Connect. Do you know how hacky and how far you can get with those? Very far, okay? And you have exactly one semantics in Flink. Well, you have it also in Kafka Connect for source connectors. So it's pretty much everything except maintenance tasks. So that really does, that kind of sucks. And also fast append. Great. All right, so which do you actually want to choose? And again, I'm not gonna I can't point to one and tell you what to use, but I'm gonna now summarize from the perspective of, we're gonna envision what your teams look like, okay? So for Spark, this is gonna be a great choice if you're already using Spark. Great, do you already know how to use Spark? Do you? Yeah, don't choose it, that's fine. If you're already running Spark jobs, or maybe your team does maintain your lakehouse and you've kind of inherited that and that's what you're doing, great, stick with Spark. If you're already doing those maintenance tasks, if you're already taking care of Iceberg, fantastic, do that. Although Flink is a close runner-up in that case, okay? For streaming, no. You'll need to ask yourself if you want to be doing true streaming, if the microbatching is good enough for you. So you can't really do a lot of topic-to-topic joins very easily in a nice, elegant way. We like elegance in computer science, so that's going to hurt your pride if you choose to do it this way. Yeah, so where I envision teams actually choosing to use Spark in this case is, yeah, like I said, you are inheriting the lakehouse, or you've been chosen to run this, and you are prompting moving the data from Kafka into Iceberg. You already are maintaining these Iceberg tables. That would make sense. Or if your team is outside of that lakehouse, that team, you're already using Spark and you feel comfortable doing that. Okay, this is going to get you pretty far. For Flink, great. You get a lot of cool things like actual streaming. We like that. It's good for CDC use cases. I've seen a lot of people opt for that in this case. We do get exactly once, and you get equality deletes, but they are trash, so it doesn't really matter. Cons, again, if we're looking at from the perspective of I am maintaining my lakehouse, you're probably using Spark anyway to do that for maintenance tasks. Do we want to add another technology to the stack in this case? You would only really want to add another technology to the stack if you need that streaming aspect, okay? So you want to weigh these pros and cons there, okay? We can get into some of these things. The cons, great, Flink jobs, hate those. Schema evolution, it's a little clunky here. Hidden partitioning, a lot of limitations in there. I don't think anybody mentioned hidden partitioning tonight, right? Look it up, it's cool. And of course, limited maintenance tasks, but they are coming. So maybe wait to move your data from Kafka to Iceberg until the Flink maintenance tasks come, right? And finally, I hope no one's actually like listening to me. So for Kafka Connect, again, I think it's the golden child, truly, okay? If you want this to be as easy as possible, probably use Kafka Connect and make it somebody else's problem to maintain your Iceberg tables. I just think that's the best possible option here. It looks cool, you get exactly once. Also, didn't mention this before, table and database fan out automatically, it's great. Schema evolution, automatically. You didn't even know you could care about that, and you don't have to, it's great. The only cons, again, is limited processing capabilities. Like if you want to do any sort of processing on your Kafka data coming in, you're limited to SMTs. You can do a lot with it, but maybe you shouldn't. And again, no built-in maintenance. So someone is going to have to do that for you. So why would you use Kafka Connect? If you are not the people that is responsible for maintaining the lakehouse, okay? But there is someone. Promise me there's someone that's taking care of your tables long-term, okay? And you're just the fun and fancy-free Kafka team that's just like, yeah, I just want to move data into Iceberg, right? That's your team, right? It's great. So yeah, so with that, I mean, now you know obviously what to choose, right? You all saw yourself in one of these personas. I know you did. Okay. And so with that was chaos. And thank you for attending my talk. Here's a link to my link tree. In it, you will find more things about Kafka, more things about Iceberg, but most importantly, Iceberg Summit's coming up in April. It's in San Francisco. None of you will go, but unless you really want to, I would love to see all of you there. You should go. You would benefit from it. It's fantastic. So it's in San Francisco in April, but we have a free virtual pass. And so one whole track, see, now you're going to sign up. There's one full track of live stream content, and all the content will be recorded and released afterwards. There are going to be a handful of Kafka e-streaming talks as well. So there you go. So yeah, sign up, watch the virtual stream. It's going to be great. And thank you. Cool.
Thank you, Danica. Any questions about Kafka?
Yeah, I'm ready. She's ready. Actually, I can punt all of them to you.
So why to use Kafka or Data Fusion, right?
Oh, man.
But my question will be related. So if we don't want to go Java space and stay in native processing space, do we have an option?
Oh, man. No, just can't do it. That's a lie.
Too late.
No, you're fine. I am 10 days jet lagged right now. So yeah, but there are options. Can I name any of them immediately off the top of my head right now? No. Andrew?
I was just trying to think. I was about to do
Oh, Snowflake. Yeah, great. Snowpark streaming. Snowpipe streaming. That's what it's called. Yep. That one. Wow. Do you work for Snowflake? It's all right. Nobody needs equality deletes. They're trash. Sorry. I know. Anyway. Anyone else?
Why are equality deletes trash? Why do you
Listen, it's because there's no bound on them. They're like unhinged chaos. They apply across the entire table. And so when you are trying to be efficient about the data that you're reading, so with positional deletes, you at least know exactly which file has the deletes that you care about. Yeah, no, that's backwards. But with equality deletes, they can apply potentially across the entire table. And so you need to kind of go reconcile those, which is kind of annoying. I don't really think, like, I haven't heard a good reason to use them, honestly.
Connector, Kafka connector will generate equality deletes, right? Because the Kafka connector cannot know exactly what position is in which, right? So it will generate equality. So if you stream with the
I know,
connector,
but they're trash.
you don't really have it.
They're really only good. The only good argument or the only good justification I heard is that streaming people like equality deletes. But I am proof that I don't like them because they're way simpler on. But then it all changes with V3, so it doesn't really matter. So huge asterisk. This applies to V2 Iceberg tables. So it's all changing in a couple months. So it's actively changing. So you have to attend Iceberg Summit to know. Okay. Yeah.
But,
Yeah.
I don't know how relevant is that, but regarding the delete files, can't we, like, when we are creating any number of smaller files, can't we use a copyright kind of thing and make it as a single file?
Yeah, but then you're doing that up front, and you have to spend that time to do that, right? So then it's added latency in the beginning, where you want to kind of punt it to you. I think the goal of computer science is to make it somebody else's problem.
The question is, why not run a compaction on equality deletes? And then you have like 1,000 small equality deletes. Just do it in
Oh, just compact the quality deletes into. Can't you do that? Don't they have a compaction for the? I'm making stuff up. Just a GitHub issue. Just add it on there. Ask for a feature request, seriously, while they're currently writing deletion vectors. It's like, no, I really want quality delete compaction. Perfect. Yeah. Well, couldn't you technically do it on your own? You could write a task. That would just be not fun. You could do it on your own. But do you want to? If you can dream it, you can build it. So. All right. He wants me off the stage.
Thank you very much. It was awesome.
We are working on this. Did you shut me off, Andrew? No. I can't find the set. Oh, no. I
So the real issue with
All right, guys. So obviously, I am the last speaker, so I will announce myself. Just give me a sec just to get inside of a StreamYard.
they just to make it as easy as possible.
We good? Perfect. Wonderful. Well, thanks for everyone who is still here for the last talk. Well, Andrew was saying that is going to be better and better, and that I hope it was exactly like he described. But my task is right now, as a last speaker, maybe to ask some questions, because you get a lot of information about Iceberg, right? So it's what I will try to ask you right now in the next couple of minutes, slides. So the first thing is about the open source. So I would love just to kind of highlight that we are here because of open source. Apache Iceberg is open source, Spark is open source, Kafka is open source, Starox is open source. So you see, like, there is something about the open source. And what I'm just trying to understand when I'm here presenting about Iceberg in front of people. So who of you is using open source? Can you just raise your hand? Oh, okay. No open source? No Kafka, no Spark, no nothing? Wonderful. Who of you contribute to open source? Yes, that's the thing. So what I would love just to inspire you guys, just look at the any open source project and try just to get into just like there are different ways how we can contribute. It's not just about to write a code. You can just go and try it out. You can just open the issue, equality deletes compaction. And then you're just a contributor to Apache Iceberg, right? So that's the idea about the contribution. You can do all different stuff. And that's something what I would love to inspire you to do. Before jumping in, I'm just want to try to understand any data engineers here? No? Data scientists? No? Are you software engineers? Oh, 1, 2, 3. Okay. So got it. Any business people? Oh, welcome. That's
I'm in the transition.
to where?
Like you just joined, like you did his MBA.
I did my MBA. I'm transitioning from the technical background to kind of business.
Perfect. So everyone who is not here from business, from a technical side, so the next time, please grab your colleague from a business side to this type of event, so they just see what you're talking about all the day long, right, in your meetings, and then they can just understand probably better. So maybe just a short introduction. My name is Victor. I'm a co-founder of a company named Bakama, and we are creator of Lakekeeper, one of the catalog, REST catalog, and we're gonna talk about the catalogs right now. And the catalog what we created is open source, and it was written in Rust. So everyone who is here Rust fan and not JVM fan, guys, here's something where you can actually contribute as well. Well, we got from Andrew a very nice drawing about the IT archaeology, right? So he started very, very, very early. So I will just try to recap. 90s, from my understanding, like data warehouse, Postgres, and we got that nice monolith that could actually do everything till some boundaries. I mean, we can argue. So TATOS, DB2 still working pretty nice. But then we've got internet with big data, and probably like next to Hadoop and Spark, Hive and Hive Metastore was probably the first attempt to get to a feeling that, oh yeah, you don't have a database, you have a bunch of files, but maybe we can somehow facilitate in front of that file a table filling to a user. So how did we do that? We just put a couple of monoliths together, called that massive parallel processing, and we've got happy. 2010, cloud data warehouse, right? So cloud happened, and then we saw, oh, it's super easy just to kind of automate the whole stuff, to provision the cluster, and that's what Redshift and Snowflake actually did. But it's not just about the automation, it's about the separation between compute and storage. And now it was kind of awesome. Oh, I now can go and store petabytes of data and provision just a small, tiny warehouse to analyze that data. And hopefully it will work. And probably I need to provision a bigger warehouse to run my analytics. Well, the community from a big data set, we can do it better. And Databricks, probably Trino S3 is like the one who is kind of like trying to do a better implementation of a similar concept, what Redshift and Snowflake did. But they went further and they said, why not separate the data? So now we have a Parquet file, and then when we can put that Parquet file on a place where we need that, and then we can provision a compute as much as we need, and then we are quite happy. So we are very interoperable in a that way. Unfortunately, what we've got is kind of like one vault with transactions and semantic and time travel, but it was probably not exactly what we expected because of a volume of data. So it was hard to manage the same volume of data. On the other hand, we've got that the way that we can store like exabytes of data, but on Parquet file, it was immutable. You cannot just go and change some stuff. You need to rewrite the whole file. And we don't have like transaction. It's eventually consistency, but it was cheaper somehow. So the idea came, so why not to create something together, something like what can be provide like the both advantages from cloud data warehouse and from a data lake, where now you have an Iceberg, and you probably already know what Iceberg is. What is Iceberg? It's just a specification. It's just for specification where you have a table view, table specification, view specification. You have a REST catalog specification and Puffin specification. Wish of luck from a community to implement the whole specification. But what is actually the thing about the Iceberg is that we've got exactly what Danica was describing, the metadata layer. Now we have that prominent metadata layer, and we are very happy about that. Well, that's was surprised that we didn't get that picture before. That's actually a proof you at Apache Iceberg Meetup, because that's the most famous.
That's why I changed it. It's so hard to read.
Yeah.
It needs to take advantage of the horizontal space on the screen.
But that's like the art.
It's art, isn't it, Alex?
It's like an art.
Oh, really?
But what you actually see, you see the catalog, you see the metadata or metadata layer, and then you have a data layer with your Parquet files, and then there is a magic on the metadata layer. Well, the metadata layer is quite interesting for us, for our company, because we're developing the catalog. And at the beginning, in the first iteration, it was like, oh, let's create a catalog which will just point to a metadata JSON file, and then we're all happy because now we know exactly how to read the current state of Iceberg. Or even if you want to have a time travel, that is what Iceberg catalog will help us. And as you can see, we got a lot of different catalogs: JDBC, Hadoop catalog, Hive catalog, Nessie catalog. And you can imagine how hard it was to adopt Iceberg, because every query engine needs to adopt this type of technology. So the Iceberg community decided, so let's create a standard, a REST specification. And that REST specification, we got actually exactly a simple way how every catalog should speak with a query engine. But again, catalog, a creative name as a metadata, right? So there's so many catalogs, and everyone is confused at the beginning. I do have a catalog. Why do I need an additional catalog? Well, it's not the same catalog. It's a technical catalog for Apache Iceberg. Fortunately, people and companies started to talk about the metastore, because catalog got more competency, because as you can see with REST, the REST catalog now is responsible to write the metadata JSON file, which is a final commit of your table. And that gives you additional thing about like how to store the Apache Iceberg table. So you have a life cycle competency on a catalog. But then if that's a place where my query engine will go and ask like, okay, where's the table? Probably I should just put a governance on the catalog as well. So catalog will tell you, well, I know where a table is, but you're not going to read that table because you don't have a right to that. So there is a central place that will allow you to centralize the governance in a decentralized world. Because what you actually have, you have a bunch of different computes, and you have probably a different storages. And then you need a simple but a central control plane that will allow you to manage the life cycle of your table, create table, alter table. It will help you to manage the access rights Paul can read, Anna cannot write, and so on and so forth. And then as Andrew was talking about the whole AI thing, so we have ML, we have deep learning agents, LLM. So how to manage actually the governance here? So no one is actually looking at that topic right now. So everyone hopes that that is going to work somehow. But exactly if LLM will go to and read some kind of Iceberg table, probably the control plane can help here with the governance. So let me just explain on a fine-grained access control how it actually works on Iceberg. So you have your object storage, you have your Iceberg REST catalog. So what we did with Lakekeeper, we made a decision not to put the authorization inside of Lakekeeper itself. We use another open source project, OpenFGA, which is a Google Zanzibar paper implementation to give you a relational-based access control. Read it, it's quite cool. But right now we have a way just to, let's say we will want to deploy everything on Kubernetes, on Docker. And in addition that your identity does not live inside of a catalog or in any system. Your identity lives in an identity provider like Keycloak, Okta, and Trade. Then we differ between different type of computes. So we have, first of all, a general compute where something like Kafka or Spark needs to write data to your Iceberg table. And then we can say, okay, that's a single user. We'll give that machine a client ID, client secret, and then they can just go and do the operation. But suddenly we have sometimes a funny system with hundreds of different users. Trino, Starox, where behind that system we have all the different users. And now it's like the question, well, how we can actually enforce the thing, because we don't have a monolith anymore. It's not a nice single Postgres database where I can say what exactly is possible. But here in that situation, I have a technical user that can read every table. And now I need somehow to enforce it. There is a solution, another open source technology, Open Policy Agent, that is some sort of a bridge function that allows a query engine like Trino to get the information on that specific user, what the permission of that user is. Here is the enterprise-ready, open source, no license, license-free lakehouse technology for you. So you can just take it and use it, and you will be able just to build a platform that will satisfy your CISO requirement. Let's do a demo. That should be a candle for a demo god, so hopefully everything works. My demo is quite simple. If you will go to a repo of Lakekeeper, there is an examples folder, and everything what you need to do is a Docker Compose app. And then everything runs, everything open source, you can just play around with that. After the Docker Compose app is big enough, maybe a little bit bigger. So you have a couple of Jupyter notebooks here just to run through. First of all, you need to bootstrap the cluster to do some operation. So you create the application itself. Then you need to create a warehouse. And here what I use is a Trino just to create a catalog inside of a Trino. It's Apache Iceberg REST catalog. And then we connect to from Trino to Lakekeeper. And then what I want to do here in that sense, I am a user Peter, and me as a user Peter, I would love to read the table. What's the table name? Products. So let me just run that. What is asking me is to make the authentication as a Peter. Iceberg. Now let's go to the Jupyter notebook, and voila, we've got the data. Let's simulate a different user. For that purposes, I have here an incognito mode. And here is user Anna. And I want to read the same table products. So running that query, making the authentication as Anna. Getting an error where we see permission denied. It looks super boring and simple, but if you go back to the technology where you have like everything distributed, you have IDP in one end, you have your policy in different, You have your query engine that does actually know about the policy, does not probably about the IDP, has no idea about the all resources. So the governance became kind of a nightmare. And here's exactly what we can actually solve, and how we're going to do that with Lakekeeper. Let me show you. So let me just go to Lakekeeper. I need to sign in. So here's Lakekeeper, and we have exactly that warehouse demo, and we have a namespace finance, and then we have a table. It was the products. And now I can just go to the table permissions here and grant Anna. No, Anna is not logged in. So probably Kendall didn't help. Here we go. And we will give Anna a select right here. So now Anna has a select right. We can actually check the status here. And what we see the warehouse, the finance, tables, and we see exactly, well, one table, not two tables as it was here in the finance, because that is exactly where that Google Zanzibar paper implementation with OpenFJ helps us to manage the governance. And if Anna will run the same query now, let's rerun the query. Now Anna is able just to read the whole thing. Similar is, let's say the Peter is not just want to use Trino, but you want to use Iceberg. And let me probably need to restart the whole thing and now to install the Iceberg. So I'm using absolutely different query engine in that sense. I'm not using Trino, but instead Iceberg, and trying just to read the same here table. Takes a while to download and to install. Here we go. We need again to authenticate ourselves, give grunts. And if you go back, now we have the data. So that is exactly like on that picture where you have like your storage, you have your catalog, and then you can use all the different query engines and solve the governance problem through the catalog, because it's in a centralized way. So let me go back to a slide. And the thing is about, like, if you see this type of solution, your manager will probably ask you like, okay, 1, 2, 3, 4, 5, 6, 7, 8, like 10 different technologies. Who is going to manage that? Is it you? You probably not. So the question is like how to simplify the things, because it's super easy to make something very complex, but it's super hard to simplify the stuff. And this is exactly where the Iceberg community is right now working on to propose the FGAC proposal to create this. And this is, by the way, where you can actually be involved as well from a community perspective, to go and maybe read it through to make the proposal somehow better. But the idea is right now just to get the whole here thing about this additional stuff, and instead to have a communication between the query engine and the catalog, and to apply specific policies stored somewhere, maybe even outside, and give you even easier way to make the fine-grained access control on your tables. Even going further to the column masking and row filtering, because always you have like a table, and that table lives like different, let's say, countries, and then you want to say like, okay, the data for island managers should be visible for island managers, and data for UK managers visible for UK. And that's something what you can achieve in the future. Not today. Today you will probably need to provision a little bit more on your infrastructure. But what we trying to think right now inside of Lakekeeper team as well. So how we can actually implement that, and to provide you even more from an open perspective. And what we implemented in our solution as well as CEDAR policies. And does someone know CEDAR? Cool. Again, it's a Rust library. We use it as well, and then it was super easy for us just to implement the CEDA policy, and it's super, super powerful what you can actually achieve with that. And just to give you an additional thing, what we thought, like, okay, so now we have a CEDA policies, and the engines like Trino can communicate with Lakekeeper, and engines Starox can communicate even directly without the open policy agent interface. But there are some engines that don't allow now this type of communication yet, probably. And the idea is, why not just to use the catalog and push that governance to Snowflake, to Databricks, to ClickHouse, and actually to achieve some kind of continuous governance experience for your platform. Because if you will go to a bigger enterprises, you will find like all the technologies in a single company. And again, if they all want to read Iceberg, that's something how we can actually provide the unified governance to every company right now. But because we have Cedar, and we had like the whole discussion about the role-based access control, the question came up, what about the attribute-based access control? And that's quite interesting, because what we can do right now, let's say we have our identity, and then that identity we can just give some claim roles, and then we have like a role on the JWT token. And what we can do on Iceberg table, we can add some properties, and one of that property can be exactly for the access. Inside of Cedar, we will just put the policy that will just apply it for attributes. And that is just right now like an explicit property, but you can imagine that we can replace that with a variable. And then we have just only a single policy that then cover like for like thousands of different users inside of your company. And everything what you need to do is to go to your IDP, put on that specific person or like identity, the role, and then the whole governance is going to be completely automatic. So you don't need to go as I did in UI and click and do the stuff, but instead it's going to be automatically done. And then you don't have like many additional tools inside of your architecture. So that's the whole thing about the governance. And the main point is about the catalog. At the beginning, it was about like, okay, how to manage the table, the life cycle. But we see that the catalog is getting more and more inside of governance, how to solve the governance, and the control plane is the idea how catalog is now changing. Well, that's it from my side on my topic. Any questions about the catalog or governance? Go ahead. Yes. It is there. It was from day one, and now we extended for attribute-based access control. I think it is.
What version are you using?
09.
Oh, everything has changed.
Yeah.
There's a lot of stuff there now.
Yeah, so there are different solutions about like how to solve the governance. Right now, what we created is permissionless code. So what you will do with a CEDA policy at the end, you will have a declarative approach. You will define your end state of your governance. And then you will more or less, if you're on Kubernetes, for instance, you will just deploy the custom resources, and Lakekeeper is capable of just sync your custom resources from Kubernetes. And you don't need to click and do stuff. It just automatically provision from your environments, from test, dev, prod, and that's a different way. Because what is going to happen, especially in the future, as Andrew has described with agents, we will get, well, right now you have a company with 10,000 employees, but you can imagine that company will have like, I don't know, 100,000 of agents. And then you can imagine that that pure person who needs to go and click and assign and grant and revoke, it's going to be very, very hard. So you need the automated way how to manage the governance. And that's how you can actually achieve through a control plane. Then no other questions. I would say thank you very much for attending. So I'm just closing the session right now. I guess we still have some time for networking. And guys, Apache Iceberg Europe community, again, Spain, Finland, well, Ireland is done. And if you want, just reach out to us. We're happy to host in whatever place you have the idea to run the Iceberg community meetup. Happy to support you on that. Thank you very much.
Thank you so much.